We stopped here last time. Still, we were talking about the casting process. This is a foundry practices and furnaces. Foundry and furnaces. Foundry is a place that we usually do the casting process. Furnaces is a device is used to melt the material and do casting process. So foundry and furnaces. A furnace is charged with the melting stock, alloy element, and various other elements. This is the melting stock اللي هي raw material. Melting stock is the raw material of the material that you would like to cast. Alloying element, this other alloying element and or additive to improve the quality of the product, and also various other material like what we call is the flux and slag. Flux and slag. This is very important. What is a flux and slag? Flux is a material added with a raw material. Material added with the raw material in the furnace, and the functionality of the flux refine molten metal by removing the solvent gases and various impurities. This is a gases. Usually there are some gases trapped inside in a liquid when we melt the material. When we melt the material, there are some gases trapped inside. This is the one thing. Another thing, environment. Some material, when you melt, it reacts with the environment and create oxide film and so on. So we added the flux. Flux is a material added and melted, definitely melted with the raw material, and then react with the environment. The functionality of the flux react with the environment, react with the gases in the liquid, and it creates slug. So the slug, this one slug created because of flux react with the gas. So when flux react with the gas, creates slag. So slag is a layer produced when flux react with the environment, and this layer usually is a very low density and float, as you can see, and they become at the top here. This layer protects the liquid metal from further chemical reaction with the environment, and also absorb gases from the liquid if there are some gases trapped in the liquid during the melting process. So this is a flux and slag, and this is very important. Very important to add flux to the raw material. If you don't add flux to raw material, usually some material or many of material, when you melt, react with the environment and create oxide film and so on. So this is the issue, right? Furnaces, there are many furnaces being used in industry for melting and casting material, but commonly we have coupled direct fuel fire furnace, curable furnace, electrical furnace, and induction furnace. This is a commonly used furnace in industry. We will focus on that, but there are also many other furnaces being used also in industry. Let's start first with a copper furnace. This is a copper furnace, and the copper furnace being used for cast iron. And you can see that this one is a vertical one. You can see here, this is a charging raw material. We're charging raw material inside, and then there are hot gases here. Then raw material here is we put not only raw material the coke and flux. coke is اللي هو الفحم يعني يا شباب بالعربي. بنحط الرو ماتيريال اللي هي الايرون فور اكزامبل, because this one mainly for cast iron. we put raw material, iron raw material. we put coke and flux. coke اللي هو الفحم, وفلكس بنحط الفلكس هنا عشان زي ما احنا we discussed earlier in the previous slide. And then we pumping here hot gases. In hot gases, very hot gases. Then the iron or the coke start firing, and then temperature increase up to the melting temperature of the iron. Then iron melting, and then become liquid, and we trap liquid here. And flux being taken from this side. Flux or slag. After slag created, slag will be removed from here, and liquid will be removed from here. Let me show you a nice video about this one. Just give me a second. right? Okay. This is a copper furnace, as you can see here. This is it is vertical, as you can see here. This is a copper furnace. This is a charging area. Charging being we put charge inside. This is the iron. This is the coke and flux together. Iron, coke, and flux. But this is made of refractory material. This is a refractory material to withstand very high melting temperature. And then bring all this charging inside. Show now. So this is the iron or metal. This is the coke. This is a flux. coke here is a element. This فحم، يعني الفحم هنا هيشتعل وبعدين هو اللي يعمل عملية الحرارة عشان الميلتنج. Now you can see that. This is a, now you see inside, show you inside made of refractory. This is refractory material. And put all inside, then all come inside. As you can see here, this is pumping here very hot gases. This is the gas, hot gases. Then you see coke here become fired, then temperature increase up to the melting temperature. Then all material will be melted, become liquid, then drop here inside. Then get liquid, melted, become liquid. Okay, slag will be created. Slag will be created at the top, and then here you take the liquid, and slag will be taken from the other side. Slag also will be taken from the other side, right? Get back to slide again. So this is a copper furnace. This is a copper furnace as I described. This is the first one. This mainly, listen to me carefully, mainly for cast iron. Why mainly for cast iron? Because here there are a coke. And this coke is اللي هو الفحم يعني. ده كربون يعني. We cannot use coke with other material like aluminium or copper. Will be like impurities. If you try to use a coke with other material, not cast iron, but with other material like aluminium or copper, it will become impurity. When it become liquid, this one will trap inside and will be very difficult to deal with this one and become impurity. But in case of cast iron, no issue, because cast iron mainly carbon. So if this one come trapped inside, meaning carbon percent will increase or something, then no issues. Then mainly this one only be used for cast iron, right? We cannot use this one with other material, only cast iron. Next is the direct fuel furnace, direct fuel fired furnace. This is another furnace. You can see it is very big also. It's 5 meters. And the difference here, this in raw material. Okay, this one you put raw material inside from here, and this one here gases. This is natural gases. We use the natural. Do you know the natural gases؟ اللي هو الغاز يا شباب اللي بيستخدموه يعني اللي هو في البيوت يعني الغاز اللي بيشتعل يعني natural gases. So this is natural gas. No coke here. We're not going to use coke anymore. So here this is the raw material. Raw material is what is raw material? Raw material means the metal that you would like to melt plus flux. We need to add flux also as well. Flux is very important all time because this one protecting the material from further chemical reaction with the environment and so on. So we put flux and the material, and here we put gases. We pump gas. We call is natural gases is fuel gases actually, and here you burn here. This is a natural gas burner. Burner means ignition. Ignition. You do ignition at this area. You do ignition. So natural gas inside, when you burn here, it's exploded. Boom, exploded. When exploded, then this one coming down, then melt here. melt. Can you understand? So it melts, then go liquid, then you trap here. This is a slag be taken from here because it's the top layer is slag, and then liquid will be taken from the other side. This one we call it direct fuel furnace, and this one mainly for non-ferrous material, mainly for non-ferrous material, such as copper-based alloys and aluminium. Copper-based alloys and aluminium, and no coke here being used. So it is mainly for copper and aluminium, usually used for copper and aluminium. Next is another type of furnaces also being used in industry, which is curable furnace. Curable furnace here, and sometimes we call it indirect fuel furnace. Indirect, why indirect? Indirect fuel furnace because there are no direct contact between fire and metal or liquid. Why? Because you can see that it is there are a pot here. We're using a pot here. This one. So we put here, and we the liquid will be inside and fire will be outside. So there are no direct. So this is the reason why they call it indirect fuel furnace. Indirect, we call it also curable furnace or indirect fuel furnace. This one usually used for non-ferrous metal like bronze, brass, alloys, zinc, and aluminium. And there are three types of this one. There are three types of this furnace. What I call left out. Left out means this one is here. This is a refractory material. This one pot is here, and later this cover will be removed, and something like crane will take this part out. That's why we call left out. So crane come inside and take this part out to deliver liquid somewhere else. This is the one we call it left out. Second one we call it stationary because this one not taken out, but this one bigger. Then also here when you get a melt, you take cover, you remove the cover, and then you bring something to take liquid from inside. You take a container, you bring container with a crane and take liquid from. So stationary. This one taken, left out. This one is stationary, remaining here, but you take liquid from inside. This one tilting. Tilting mean when you finish, you tilt. You rotate this one, then this one will be tilted. Then you drop liquid in something and you take it to do the casting somewhere else. Three type. And this one mainly for non-ferrous material, bronze, brass, alloy, zinc, aluminium, and so on. This is another type of furnaces being used. You can see that sometimes big furnace, sometimes small furnace. It depends on the foundry itself. Some foundry are specialized in a cast iron, having curable furnace. Some other mass production with aluminium and copper and so direct fuel furnace. Some other foundry, small foundry, casting bronze, brass, and alloy zinc using this one, which is a curable furnace. And also we have electrical arc furnace. This is also very big one, and also this one is expensive. This is one electrical arc furnace. This is mass production electrical arc furnace. Big company uses this one usually. And this one also here, same, all furnaces, when we talk about furnaces, all charging the raw material plus flux. Then you have to understand that this one usually used in melting steel, because this one can control the environment. This one usually melting steel. This is high power being used here, and this one usually using for melting steel, because if you remember that we said that melting steel is an issue, because steel not only high melting temperature material, but also material oxidized at higher temperature, then need the control of the environment. This one can control the environment. Then this one usually used for melting steel, not cast iron but steel. And there are electrical here, electrode. This is electrode being used. This is electrical electrode, and this is the body of the furnace made of refractory material. And this is a liquid here, and then you apply electricity between electrode and the furnace, and then once this one touch, here usually is short charging of electricity happen here, and electrical short happen, and charging or discharging of electricity happen here. When discharging happen here, temperature this is electrical energy, waste of electrical energy changed to thermal energy. Then temperature increase up to melting temperature of the metal here, and then when you complete, will become liquid. Then you tilt this one. Slag will be taken from here, and liquid you tilt like this first. You take slag, remove slag, and then tilt other side. You take the liquid. Okay, let me show you a video about this one also as well. Just give me a second. Right. Okay. This is the electrical furnace. You see that in electrical furnace now we're charging. Yani put the raw material. This is the raw material and the flux, right? This is the cover. This is the electrodes. This is the furnace is closed now, and this is the electrodes. Usually graphene electrodes to withstand, and this is the charging now. This is a discharging of electricity. Then when discharge here, electrical energy becomes thermal energy, and then heating and melting. This is the up. This one is slag. This is the slag. This is the liquid. This is a slag. Because here, why slag? Because flux react with environment. This is full protection. Then added more charging. Then now added more charging, and repeat again the process. More charging, more here. This is helping. This one helping. This is the inner gas to help the process. And then the process completed. Then now we tilt this side to take slag out. This slag, we remove the slag, and then tilt the other side to take the liquid metal. So this is a liquid metal, and this is now this is the liquid. Then you do the casting process. Then steel is transferred in the casting machine. Take to the casting machine and do the casting process based on that. Yes, Muhammad.
Doctor, can you post the link of these videos in the Blackboard?
Yes, can definitely. Why not? Yeah.
يعني من كويس نرجع نستفيد منها مرة ثانية.
Yeah, exactly. This is good. And all this kind of video in YouTube actually. I bring it from YouTube. You can search actually, but yeah, I can. Yes, I will do. You know what's better to put the link here? Put link here in the slide. Yeah, I will modify the slide and put the link. So in case I put the link here, then you can just click. Once you click this one slide, then you can see the video. Right, so this is electrical arc furnace, right? Any question? Is it clear? Okay, that's it. So go further. Another one is induction furnace. It's also been used in industry. It's very common also in industry, even using electrical energy, as you can see here. So this one induction. We use here induction current. Induction current when you have a coil like this coil. Can you see that? This is a coil. Coil is rotating around. This is the furnace body. This is a furnace here, and this is a coil. If you have a coil like this and you rotate or you circulate electricity in a coil, then this is a field. Induction current field will be created. Induction current field will be created, as you can see here. This induction current will excite the atom in the raw material. This is the raw material. Then when you pass current here in the coil, then the induction current field will be created, and this induction current will excite the atom. You understand me? Excite the atom in the raw material. Then highly excite atom in the raw material, make high friction between atom, something like hardly colloid each other, and high friction will be created between the atom, and then this one highly increase the temperature up to the melting temperature. على فكرة احنا بنطبق ده يا شباب في حياتنا. يعني في كويل زي كده بيغلي الووتر. يعني في كويل احنا بنحط كويل الكتريكال كويل في الميه. مش عارف انتوا استعملتوه ولا لا. There are a coil you can just get from the market. You put in the water. In this coil, simply you put in the plug, electrical plug. Then what happened? Electrical just goes through or pass through the coil. When pass through the coil, induction electricity or induction current will pass through the liquid and then excite the atom of the liquid up to increasing the temperature up to the boiling, and then we boil water. This one people commonly use also as well. Anyway, we're using here in a furnace to excite the atom in a furnace, and finally we have this one melted, become liquid, and then we, as we just described earlier, also can be this one also melting steel, cast iron, aluminium alloys, high melting temperature material can be melted here, and this is very common also in industry. There are also another video here related to this one. Let me show you. Okay. Right. This is a furnace. This is a coil. This is a coil around. This is a furnace. You connect with the electricity. Then electricity will pass through the coil. This is the charge. We're charging the furnace. Charging means raw material and the flux. Huh? It is clear. Huh? When you said charging, mean both raw material and flux. When you start activating this one, you pass here the current here, you pass current through. Then this is, as you can see, induction current. Induction current pass through here, start exciting the atom here, then start become liquid. Then liquid will be created. Slag also will be created. You take slag out and take the liquid out. Then you get the bar done. Yep, I hope it's clear. Okay, let me go back to slide again. This is induction furnace. This is the induction furnace as we describe here. This is a furnace being used in industry. When you talk about the boring, cleaning, and heat treatment, there are many ways for handling this process. There are a crane handling, and there are two-man handling. Crane handling means there are a hook here. This is the hook. Then the crane will come here and take this one. Then crane يعني الونش يا شباب بالعربي. ونش بيجي ياخد الجزء ده فيه الليكويد يعني ياخده يوديه فين يوديه مكان تاني where casting will be done from the furnace. Then crane handling بيجي الكرين ياخد البوت دوت وجواه الليكويد, then take it to the casting area. And also manually, I think you saw the video previously, there are a manual, two-man here, two-man holding this one with the liquid, and manually, then you can do manually or using crane. This is the handling. When you come to the here, this is additional process should be done after solidification. What additional process? Additional process, which is the trimming. Trimming. What is the trimming? Trimming here, you can see that this is the part being casted, and this is the spiro, this is the runner, and so on. You need to cut here because this is the part that we would like to have. This is external or additional liquid or additional part will be done because of it is needed as a spiro, runner, and so on. We need to cut here. We call it trimming. Remove the core. If there are a core and inside, then you have to remove. So trimming and remove the core inside. Surface cleaning, to do cleaning here, to do cleaning for surface because there are many sand coming out and so on. An inspection mean to check the dimension and so on. Probably repair if required. Maybe machining if required. Maybe you need to do machining, may need to do repair. Heat treatment, probably you need to do heat treatment, which is another process later after the shaping, and then property enhancement, which is the heat treatment. After shaping done, probably you need to do heat treatment to improve the mechanical or physical properties of the product. Okay, defect in the casting. Defect in the casting. When you do casting, there are some possible defect could happen. Right? We discussed that earlier. When you do casting process, there are a possibility that there are some defect happen. International Committee of Foundry Technical Association describe the defect as metallic projection, cavity, discontinuity, defect, surface, incomplete casting, incorrect dimension or shaping, inclusion. This is the possible defect could happen in the casting based on the International Committee of Foundry Technical Association. Let me show you one by one. Let's discuss one by one. this defect one by one. You must be familiar, as an engineer, you must be familiar with this kind of possible defect. And not only that, but you have to also know how to deal with this defect, or to how to avoid or how to eliminate this defect as well. The first defect is the penetration. Penetration when fluidity liquid of metal is high fluidity here. Then the issue is here. Fluidity of liquid is high. Fluidity of liquid is high means that material have very high fluidity. Probably you heating the material to very high leak temperature. The boiling temperature is very high and the fluidity has become very high. Diffusion happen. This is the sand. It happened in the sand. Also sand casting, mainly in the sand casting. So this is a sand. Then diffusion happen. Liquid will diffuse in the sand. Sand also diffuse in the liquid. Then you get layer of mix between sand and liquid. So what is the solution? You have to, the boiling temperature must choose or select boiling temperature. Actually, there are a recommendation for the boiling temperature you have to follow. If you exceed, probably this one will done, which is this kind of problem. Second is the hot tear. Hot tear, this is the hot tear I think we described earlier. When you have a hot spot, hot spot happen when you have bigger dimension and small dimension. When you change from bigger dimension here, mainly here, and solution actually we described earlier, if you remember, to put external shell, or not only external shell, all you have to manage the dimension, to change the dimension and somehow to not just make a drop change. So, or simply you added external shell to avoid having this kind of tearing defect. We have also what we call is a cold shot. Cold shot meaning the liquid premature frozen. So liquid you fill here, the liquid will move around and then supposed to fill everywhere, but you can see here it is not completely, it is solidified because fully diffusing each other. And this happened due to probably heat transfer is high here and the dimension is narrow, dimension here is small and surface tension is high. Material don't move, fluidity is not that good, and material don't move smoothly to fuse in each other and stop here. We call it premature fusion. To solve this problem, actually, there are many ways. First, you need to increase the pouring temperature. Pouring temperature, because fluidity is not good. This is the first one. Viscosity is high. Second, here dimension here could make it bigger, a little bit bigger. You have to make it a bit bigger. So easily material, liquid will fill here and fuse in each other. This is a solution how to avoid, right? If you have such defect. This one also shrinkage cavity. This one happened due to material solidify earlier in outer surface, inner surface become liquid. This also we discussed earlier before, and then you probably get void inside. You need to do directional solidification. Probably you need to add a shell here. Probably you need to add a shell here to absorb temperature from this area to quickly solidify earlier before the outer surface. Then you can do whatever we call directional solidification. Shrinkage cavity. This is also is same. Also, this is the directional solidification. External shell being added here to solve the problem of this kind of cavity happened due to the hot spot. This is a hot spot. Then directional solidification required to solve the problem. This one we call it as sand plow. Sand plow mean the gas trap inside. Gas trap inside. You can see this is actual photo. This is a defect you can see. Probably it is on the surface. Sometime below you cannot see by eyes, by the way. Sometimes the surface, the outer surface is excellent, no issue. And this defect could be here inside. This is mainly in sand casting. This could happen because vent is not perfectly done. Vent is a tube that we make to escaping the gas is not perfectly done. You have to create vent, mini vent actually, You have to be sure vent is done perfectly in a correct position. So if not, then some gases probably coming from the moisture, coming from the burning of the sand or something trap inside and create a cavity, as you can see. So we need to avoid having this one by creating vent. Also, permeability of the sand must be, allow gases must be using different sizes of the particle of the sand, and allowing also gas to trap in case of vent not working properly. So avoid having this problem. Also, this one we call it is a pin shot. This is a pin shot or pinhole, is a function of a small gas, very, very small gas, like making like porosity. It's coming usually below the surface. This is coming from usually turbulent flow. If there are a turbulent flow, it's not a gas bubbles, but it is like small gases. This small gas like porous. Then you get the cast like porous cast. It's coming from the turbulent. If there are a turbulent flow and the flow is not perfectly adjusted as we described also earlier, then probably this could happen. We need to avoid having turbulent flow. This is a misrun. Also misrun is a fluidity is not very good. Then it is premature frozen. Premature frozen mean يعني بقى solid early. يعني حصل له solidification early. Need to fill this one. So it doesn't fill perfectly the cavity. This is a misrun. So this one fluidity is low. We need to increase the fluidity, increase the boiling temperature probably, or dimension here is very small. Then we need to make the dimension here bigger. Then here you can see this is the part with the misrun, so it's not incomplete actually, as you can see. This is a gap run out. This one I show you before, if you remember. This is because of the bouncy force. Due to the bouncy force is bigger than the weight. Then this one open and liquid spill out. Then you get this kind of gap run out. You can see the flash is created here. This one we can avoid by having clamping force here in the mold, right? We can having clamping force in the mold, right? Cold shot. This one is impurity. This impurity actually it is the same metal, but what happened is at the beginning the boring rate was very slow. Then it's kind of like droplet of liquid coming and then immediately solidify, and later liquid come. Since this liquid solidify here, creating a harder part inside the material. Then to solve this one, you have to pour the liquid at a fixed rate from beginning. You have to pour the liquid at a fixed rate from the beginning to avoid having this kind of metal splatters during the pouring. Metal splatters during the pouring. Then this one can be avoided. Finally is mold shift. This is the cup and drag. If you not align the cup and drag perfectly aligned, it must be aligned. Cup and drag must be aligned. If not aligned together, then you get shift here. Shift between cup and drag, and finally when you do casting, get something like this. This one we need to avoid aligning cup and drag when you assemble cup and drag together. Okay, this is a possible defect in casting process. Casting alloys. Casting alloys, there are many alloys. Actually, I told you before, any material we can melt, we can cast. You agree with me? Because what is the casting? Casting in a very simple way is a melting material, pouring material in a cavity, you get the cast done. So as I told you, any material you can melt, you can cast. But some material, we call it is a castable material. Some other material, we call it is a difficult to cast material. So castable material, we prefer to cast, which is easy to melt and cast material. Some other material, very difficult to melt and hence very difficult to cast. We don't prefer, or people don't prefer to cast such material. So the castable material or common castable material, ferrous and non-ferrous. The following is what we're going to describe here is the castable material. First is the ferrous material, cast iron. Cast iron is the most important alloy in casting. is the most important alloy in casting. Why? Because cast iron have reasonable melting temperature, have very good fluidity, not react with oxygen at a higher temperature. Shrinkage allowance here, or shrinkage of the cast iron, very little. Then cast iron is excellent material. We call it even cast iron, excellent material being used in the casting. The most of the casting, the highest percent of the casting in the world is usually cast iron, like gray cast iron, medium cast iron, white cast iron, malleable cast iron, alloy cast iron, and typical boiling temperature usually 1400 degrees Celsius. Second is steel. Steel actually is difficult to cast material. One of the materials that we said it is difficult, but it is also being used in casting because steel is very good material, or very excellent mechanical properties material. So casting steel, mixing complicated shape with excellent mechanical properties is really needed. So people also would like to cast steel, even casting steel have many difficulty because of this one, poor fluidity. Fluidity is very poor. Then you have to heat it up to very high melting temperature, and you have to make dimensions bigger. Also, steel oxidize at a higher melting temperature. Make casting steel really very difficult. Need to as an electrical furnace, or using induction, very special furnace to be able to control the environment. But still, people also interesting also is because even with this difficulty, people also still interesting to cast steel. The melting temperature or boiling temperature usually 1650 degree, and this one also being used in as a material for casting because of excellent mechanical properties. Aluminium also very castable material. We call it very castable material because the melting temperature is very low, which is 660 degrees Celsius. Aluminium been used in very wide range application in industry. The low weight to very high weight to strength ratio, easy for machining, soft material, being used in very wide range in the application, and cast aluminium is very considered as a very castable material. Copper and the copper alloys, bronze, brass, aluminium, bronze. Also, this material being casted or commonly casted in industry. It's being used for corrosion resistance, attractive appearance, nice appearance, and good bearing quality. Good bearing quality means strength is very reasonable. Limitation, high cost of the copper. That's why it's being used as a copper alloys. Not pure copper, but because copper is expensive, they use as a copper alloys. Bronze, brass, and aluminium bronze. Application, very wide range application like pipe fitting, then electrical application, in electrical board, in wire, pump, and so on. Several application. Zinc alloy. Zinc is also very important, being used mainly for food industry. And zinc here highly castable. We call it highly castable, commonly used in die casting, because you remember die casting? Die casting is very suitable material to be used with the die casting, mass production, easy to cast, been used in a machine and automation and so on. Melting temperature is very low, 419 degree. Good fluidity and easy for casting. Low creep strength, and this is a material low creep strength. Casting cannot be subject to prolonged high stress. This is the only issue with this one. The creep strength mean you cannot just apply stress for long time, because the dimension become to change when you apply stress for long time for zinc generally, but it being used for also wide range application in industry. Product design consideration. There are some consideration we would like to observe during the design of casting. First, design consideration we would like to always keep in mind while we designing the part for casting actually, which is a core. Core actually generally core is a complex. Core is a complex. It's better to avoid having core in the casting. It's better to avoid having core in the casting. However, if no way, then you have to have it. But in case, I said in case, you can eliminate the core from the casting, it will be better. So we call it simplified making. So for example, if you have something like this, then this one, it will be core. Then this one is better to eliminate. Then if you can change the design like this, eliminate having core inside, it will be better. But if no way, then probably you have to just go through, even it is complicated, but you have to go through. This is the first observation. Second observation is regarding the whatever we call is sharp corner. Don't ever create sharp corner in a design of the casting, because this sharp corner is very high thermal residual stress will be applied in this sharp area. So it's better to make it smooth. Yani instead of having sharp corner here, to make it like this. Don't make it sharp. This is poor, this is good. Somebody said, I would like to have this one at the end of the day, not this one. You do machining. You can just create this one by casting, and later you do machining and create this one by machining after casting. So this one, to avoid here having high residual stress concentration in this area, this one leading to defect later. Also hotspot. Hotspot, as we described earlier, this is a small area, and then a big area here, then you get defect. Definitely you will get defect here. 100% for sure you get defects like here, like here. How to solve this one? This one you can solve, for example, like this. This one you solve like this. Then the big difference between this one and this one, here you make it round, and then you make the area is almost same. To avoid jump from small area to big area, you get defect here, you make it like here. Someone else said added external shell. Can another way is to add an external shell here to absorb the heat, like heat sink, and finally can just solve the problem. But if not, then you can just do this way. If cannot, then add an external shell here, here, here. You change the design for here, for example, instead of like this, then make it like this. To not having a big dimension here, then instead of like this, make it like this. Is it okay? Somebody said, okay, can. Someone said, no, not okay, cannot. It must be like this. Then, okay, then put shell, external shell. If you cannot change the dimensions, then external. So this is kind of design consideration you must keep all time. Also here, this is kind of void. This kind of void cavity here happen. Then in case of like this, you see here big dimension. You can make it like this. If you can change like this, it would be better. Someone said no, then put shell. External shell here, external shell here. If you can change the design and make it like this, I mean smooth, and make all dimensions the same, better. Here also, this one big. You can make it like this, it will be better. Because this one solidify later, then make it smaller, so solidify earlier. Also here design consideration, here dimension. So you can change the dimension to avoid like this, it will be better. Here also cavity happen because of dimension. You can put added external shell. This is a shell. This is the external shell to absorb the heat from here. It will be better to avoid having this kind of defect. Same also here, dimension here are equal. This is dimension, some big dimension, small dimension, you get cavity immediately. Then it's better to change to this one, dimension is almost same everywhere, to avoid having cavity. Otherwise, big dimension, small dimension, you get cavity immediately. Here also, this is one like this, you make it like this to avoid having cavity, right? So cavity will be here, then you have to change to avoid cavity. This is kind of recommendation. This is the kind of recommendation in a casting you have to keep in mind all time. This one, similarity. This is the part here in, you can see that this is the part. This one very difficult. This one very difficult. You need to cut twice. Then this one, no way to cast in this one, because here how to put sand here. You need to put sand here. If you put sand here, how you take this one part out? Probably you can make lost foam. Lost foam is okay, but if you would like to make some casting with a pattern, How to put a pattern? If you put a pattern, you put sand here. How to take the pattern out and be difficult. Then they said that you cannot just make this design in this way. You have to change the design in this way. But however, if you would like to make it like this and you have to do it in this way, probably lost form is a way. Lost form can do it, because lost form you don't have to take the pattern out. You put the pattern inside, you put the sand everywhere. So most complicated part can be done by lost form, but in sand casting probably design must be changed to like this. Or if you would like to make this one in sand casting, you may make it vertical and cut twice and put up and down. Yeah, anyway, you must have to consider this one is a complication in the casting design. Right, dimension and tolerance. This is the last part in this chapter, which is a dimension and tolerance. Actually, there are what we call is draft. Draft in the design we make what we call draft. In the design we make what we call draft. Draft means taper. When you design, this is the pattern. The pattern, you put the pattern in the sand to create the cavity, right? You put the pattern in the sand to create the cavity, and later you take the pattern out. You agree with me? This is what we discussed before. However, they said that it's better when you create the pattern to make it taper. Don't make it like equal side or parallel side. Just make it like taper. Why make like taper? Easy to take the pattern out. Easy to take the pattern out from the mold. So make it like taper here. We call it draft. Draft. This one we call draft. This angle, the angle of this taper is 0.5 to 2 degrees. It depends on the material you cut. This what we call is the draft. This is draft in the pattern. There are some allowance we must consider in the design. There are some allowance we must consider in the design of the pattern. When we manufacturing the pattern, we need to consider some allowance. Some allowance mean dimension change. We need to consider that in the dimension of the pattern. So you ask me, the dimension of the pattern will be bigger dimension of the part? Yes, it is. Because the dimension of the pattern must be bigger. Later, shrinkage will happen. Shrinkage will happen means that we need to make it bigger dimension. So when shrinkage happen, it gets smaller dimension. Then you need to make the pattern bigger. So the pattern must be bigger because later will shrink. When shrink, the dimension will become smaller. If you make it exactly same as shrink, then this one will be unacceptable, will be rejected. Then you must consider the shrinkage allowance. So this is the shrinkage allowance. Okay, what else? So this is the shrinkage allowance. What else? Machining allowance. This is the machining allowance. Machining allowance because after the part finished, completed and solidified, you need to do machining. You need to remove the layer, outer layer. Why you need to remove the outer layer and inner layer actually? Inner layer, if you have a hole, you need to remove the inner layer. If you have the solid part, you need to remove the outer layer. Why? Because this layer, especially in sand casting, is mix of sand and what? Sand and liquid. Then this layer must be removed here, especially in sand casting. This is a machining, so we call machining allowance. And finally, draft allowance, because you need to add this kind of taper in the pattern to easily taken, the pattern taken from the sand. So 3 allowance must be considered while you manufacturing the pattern. One by one. First is machining allowance. Machining allowance, you need to add it one by one. We added machining allowance, we added shrinkage allowance, we added also draft allowance or taper allowance one by one. So machining allowance, this is a part that you would like to machine. This is the dimensions that you would like to have. This is the dimensions that you would like to have at the end of the casting. When you finish casting, machining everything, this is the dimension. We need to add it. So for example, if you machining cast iron, if you casting cast iron, they said added 3 millimeter in all surfaces. When you add it, it's kind of recommendation. For aluminium, another dimension. For copper, another dimension. For cast iron, 3 millimeter in all surfaces. This is an example. Then you need to change the dimension of every length here, 150 millimeters, this is 75 millimeter, this is 100 millimeters, this is a 50 millimeters, this is 200 millimeter. All dimension need to change. So 100 millimeter, 150 millimeters, this one is a diameter. Diameter, then you need to add it. This is 3 millimeter because he added here 3 millimeter this side and 3 millimeter. Because you do machining, you remove the outer layer. You remove 3 millimeter from here and 3 millimeter from here. Then 6 millimeter in radius. Then you get 150 plus 6, you get 106. Then this one change, dimension change, become 156. Then become bigger. You can see that become bigger. 100 millimeter. This is 100 millimeter is the diameter. Then 100 millimeter become plus 6, you get 106. This one 75. 75 is the internal dimension. Internal dimension, if you look to the internal, it's the whole dimension. Whole dimension you must make smaller because when you do machining it become bigger. Then 75 you must make it minus 6. I need to get 75. I need to get 75. Then you have to make 75 minus 6, so it must be 69. Become smaller, 69. So when you do machining, then it will become bigger, so it will become 75. Okay, be careful. So the outer surface, then you added. The outer surface you added because when you do machining, it becomes smaller. But inner surface, you must subtract to make it smaller. When you cut, they become bigger. And 200 millimeters, this is a 200 millimeter, this is a 200 millimeter. 200 millimeter, which is this one, become 206 because you need to do machining on this side and you do machining on this side. So you added here material. 50 millimeter with this one 50 millimeter. You need to do machining on this side, you need to do machining on this side, become 56. This is the machining allowance. This is very simple way. You need to add the machining allowance. So again, the outer surface here, you need to make it bigger. Inner surface, you need to make it smaller. Outer surface here, you need to make it bigger because you remove material, becomes smaller. Inner surfaces, you need to make it smaller because you do internal surface cleaning or surface machining here, it will become bigger. So be careful about that. This is a machining allowance. Next is shrinkage allowance. Actually, time is finished. I have to stop here.